Welcome back to this class of electrochemical studies, where we are talking about some cells, electrochemical cells, and how those electrochemical cells can be applied for your voltage generation or the electricity generation as well as the electrolysis. So, we have seen that in the electrolytic cell, the direction of the current is the reverse to that of an galvanic cell. So, that is why the definition is completely different for electrolytic cell and the galvanic cell. So, if we have the galvanic cell and the electrolytic cell, so definition for anode and cathode will be different, and anode is required that in one particular case that the anode is for the oxidation and cathode is for the reduction. But if we do in a different way, that means if we draw the electricity from there in the galvanic cell, the anode will supply that particular electrode or cathode will accept that particular electron. So, in a reversible cell, now we consider a reversible cell where we get a particular type of reaction. That means, if we see that silver is there, silver 0, which is losing electron to get silver ion for its half cell reaction. So, if some condition can be applied to it such that you can reverse the reaction, though we know that is the natural tendency for this is that if we find that there is a natural tendency for this reaction or half cell reaction. So, this is your half cell reaction, and for half cell reaction itself also we have a natural tendency. If we consider these two together, we consider that silver 0, which is kept in presence of silver ion, that whether your silver will go for oxidation to silver ion or silver ion will accept the electron to give you the silver in the metallic state. So, this whether we can reverse it, if we consider that this is one electrode reaction, the other electrode we can have. So, we get combination of these two electrodes giving rise to the corresponding electrochemical cell. So, if we have a reversible cell, reversing the current reverses the cell reaction. That means, the direction of the current in one particular direction we go for the supply of electron. If we reverse that, if we supply electron in the other electrode, we get that the reversing of the current reverses the cell reaction. That means, if we go for silver 0 to silver ion, if we reverse it, silver ion will go to silver 0 for a particular reversible reaction. But there are some electrochemical cells which are not considered as reversible cells. So, what those cells we will consider, we will name those electrode cells as irreversible cell, and this irreversible cell will behave or will function in a different manner compared to your reversible cell. When we reverse the current direction or when we reverse the current causing a different half reaction to occur at one or both the electrodes. So, we can force it such a way that we reverse the direction of the current to be passed to the two different electrodes, but if it is a irreversible cell, we will not be able to get the same reaction what we are expecting for a reversible cell, but a different type of reaction. That means, the course of reaction will be different at least for one type of electrode, or sometimes it is true for both the two electrodes. Such as what we know that the storage battery for automobiles, what we use the lead plates, the metallic lead plates and the sulfuric acid. We know that the lead is responsible for its oxidation, and something will also there which can be responsible for its reduction. But here we have a series of reversible cells, that is why it is considered as a storage battery. That means, that during that particular reaction, that means the reaction of the acid with that of our lead plates give rise to some energy. So, when energy is we are drawing and is basically discharging the thing, and its energy potential or the current potential or the voltage potential for that particular case is decreasing. So, when we draw more and more current, it is almost dying that particular battery, but when the external charger or the generator, if we put into the charging device, so the charger or the generator charges the battery, its cells are electrolytic. So, when we charge it, the cells will be electrolytic. It is not a voltaic cell, otherwise it will be a voltaic cell when it gives us the power or the electrical energy. When it is used to operate the lights, headlights, the radio or the ignition, the cell is galvanic. So, we see that is a typical example. When we draw the current, it is the corresponding galvanic cell, but when we charge it from external source of electrical energy, during the charging process, it is the corresponding cell will be termed as the electrolytic cell. So, that gives us a very good idea. So, the definition wise, the definition for your anode and cathode will also be different if we consider whether we are talking in terms of a galvanic cell or in terms of some electrolytic cell. So, thus we get some electrode, and electrode is dipped inside a solution. So, we will be able to develop some electrode potential. So, what is that potential? It is the potential of a cell. It can be your half cell also, that has a standard hydrogen electrode at the left electrode. So, if we put a standard hydrogen electrode as the left electrode, and the measured electrode potential will be the corresponding potential for its half cell reaction. So, from our school days also, we know that the corresponding level we consider the corresponding E0 value for the hydrogen electrode. Hydrogen electrode is the corresponding reduction of hydrogen 2 of H plus is reducing to hydrogen gas. So, this we consider, this particular potential we will consider as 0.0 volt, and why we consider this as 0.0 volt is that we can have some electrode what we consider as normal hydrogen electrode NHE. So, with respect to the normal hydrogen electrode, that means you have the hydrogen as the gas, and at activity 1 of this hydrogen ion, that means the corresponding acid solution. So, activity of that acid solution is also 1. So, we get that on a platinum electrode. So, that platinum electrode gives rise to the corresponding setup for hydrogen electrode. We get and based on this particular half cell, that means the tendency of the hydrogen ion for its reduction to give rise to the hydrogen gas is considered as the standard as 0.0 volt, and with respect to that we have all other species we label it. That means whether the species is have more or less electron transfer activity or tendency compared to your hydrogen electrode. So, that is why some of these metallic species or the other non-metallic species will be above this hydrogen electrode or will be below the hydrogen electrode, depending upon their tendencies for oxidation or reduction reactions. So, if we consider that whether if you have a half cell reaction of silver plus and silver 0, we have a half cell reaction. So, how we get the corresponding standard electrode potential of this, that means the E0 value for Ag plus Ag 0, how we get that. So, since by definition we are considering that we will be talking in terms of the corresponding electron transfer reactions with respect to this hydrogen electrode, that means this tendency is a standard tendency whether it accepts electron or donates electron to produce hydrogen ion from the hydrogen gas is a reference one, and with reference to that whether your this half cell, the another half cell will be oxidizing or reducing, that will tells us whether it will be above this 0 level or below this 0 level. So, if we connect this particular one, if we connect this cell, that means the cell for your silver ion, that means we are talking in terms of the corresponding reduction reactions, because all these cases will be reporting. This is the natural convention or the standard convention is your reduction potential. So, what will be reporting is your reduction potential. So, this will give rise to silver 0 is the typical reduction reaction. So, that reduction reaction will tell us, and how we measure this E0 value is that is very simple, that you connect it with a standard hydrogen electrode as your left electrode. So, the species whose E0 value will be measuring is on the right and the hydrogen electrode will be the left. Then we get the standard electrode potential as your E0. As a half reaction is defined as the electrode potential when the activities of the reactants and products are all unity. That means, this hydrogen gas, if we consider this as the hydrogen electrode, is at 1 atmospheric pressure. So, this has the activity of 1 and hydrogen gas is also bubbling on the electrode platinum electrode surface, having a potential of 1 atmosphere. So, we get these as activities of the reactants and products are all unity. So, if we consider their concentrations in that particular terms and the resulting E0 value, what we will be getting over there is your E0 value for that particular half cell reaction. Now, we will take 3 consecutive reactions or 3 reactions we will consider. One is the reaction of acid with cadmium, solid cadmium, that means the cadmium in the metallic state, cadmium in the 0 state, giving rise to the evolution of hydrogen, and cadmium is going to cadmium 2 plus. Then the second reaction we will be considering is as your silver ion, which is reacting with H2 gas, giving rise to silver as a silver solid or silver 0 or the metallic silver and hydrogen ion. And third one is the reaction between cadmium in the cadmium ion, the ionic state of cadmium, that means the cadmium in solution, and zinc is very similar to that of our thing what we are discussing from our previous class, that the dipping copper rod or the copper spiral wire inside a corresponding silver solution will resulting the corresponding deposition. Similarly, if we dip zinc rod within the cadmium solution, cadmium will be deposited and zinc will go into the solution. So, in terms of electron transfer reactions, and all are interconnected, hydrogen is connected to cadmium, the same hydrogen is connected to silver, and then cadmium is again connected to zinc. So, if we consider out of these 3 reactions the 4 species, that means hydrogen, cadmium, silver and zinc, and if we try to consider their relative tendency for oxidation and reduction reactions, that we should know very nicely from the reaction if the reaction goes from left to right. Though we have written these in the reversible sign, but what we are considering that it has a tendency. That is why initially when these two are reacted, that means cadmium is reacted with some acid, the reaction will go to the right hand side with the evolution of hydrogen, that means cadmium is the stronger reducing agent which can reduce your hydrogen ion for hydrogen gas evolution. So, until and unless you have the corresponding evolution of these things, and if we keep together we reach the corresponding concentration, that means the equilibrium concentration. When equilibrium concentration is reached, H2 further react with cadmium 2 plus, producing back your cadmium solid and the hydrogen ion, but that is not happening when it is beyond or when it is away from your equilibrium situation. Similarly, for the second reaction also, when we start from the left, we are beyond some equilibrium situation, and as we proceed towards equilibrium, your reaction is in the reverse direction. And third reaction is also in a similar fashion. So, if we try to go for these reactions, so what we will be looking for basically, we will be looking for something where we will be considering for these half cell reactions. That means, what should be your E0 value for these, which is very important to know, and as we defined already by definition, this is 0.0 volt versus NHE. So, what will be the other cases, that means involvement of this, then we have the corresponding silver ion, that means silver ion silver 0, then we have cadmium 2 plus and cadmium, and zinc 2 plus and zinc. So, what are these values? So, by looking at the reaction, we can have some good idea about the tendency. That means, if we consider these are the pairs, on the left you have the species which can be reduced to the species which are on the right hand side. That means, all 4 species on the left can be reduced to all 4 species on the right. So, the electron transfer reaction or the tendency for some of these species, that means, if we consider these the cationic species altogether, which will be accepting electron, that means, their corresponding reduction potential values, or in the reverse way, if we consider the species on the right hand side, their oxidizing capability, that means tendency for accepting the electron. So, this tendency for accepting electron by going from H plus to H2, Ag plus to Ag, Cd 2 plus to Cd and Zn 2 plus to Zn will tell us the corresponding potential in terms of its E0 values. So, by looking at these things, some important information we can gather without knowing the quantitative magnitude of E0 values is that if we consider that first reaction, the first reaction what it tells, this is the corresponding reaction of H plus with cadmium, metallic cadmium. So, first reaction demonstrates that H plus is more effective than cadmium 2 plus in terms of its electron acceptance. That means, its corresponding electron acceptance is that it can function as the corresponding oxidizing agent. That means, we are talking in terms of the corresponding oxidizing strength of all these species. So, what we are looking for? We are looking for 4 species and their corresponding electron acceptance behavior. If the electron acceptance behavior is considered in terms of its oxidizing strength, we try to have some order for 4 different species. So, the first reaction will tell us that H plus is more effective than cadmium 2 plus. That means, H plus will have more tendency to accept electron from cadmium, and cadmium will go into the solution as cadmium 2 plus, and H plus is the stronger oxidizing agent to oxidize the cadmium 2 plus to cadmium 0 to cadmium 2 plus. So, proton, that means acid, is your oxidizing agent. Why this acid is oxidizing agent? That means, in presence of cadmium, the acid will be responsible for evolution of hydrogen. Similarly, the second reaction tells us that your Ag plus, that means the silver ion, is more effective electron acceptor than H plus. If we go for a competitive situation, that means whether silver ion will accept electron or H plus will accept electron, it is the silver ion which is more effective in terms of its electron acceptance. So, we get the oxidizing strength order as Ag plus is greater than H plus. And third equation shows that the cadmium 2 plus is more effective as oxidizing agent than zinc 2 plus. That means, if we consider the corresponding oxidizing strength of cadmium 2 plus, bivalent cadmium and bivalent zinc, we consider that cadmium will be stronger oxidizing agent compared to zinc 2 plus. So, cadmium will be responsible for oxidation compared to your zinc 2 plus. So, if we arrange all together, we get this particular order where silver plus is greater than H plus is greater than cadmium 2 plus is greater than zinc 2 plus. So, in a qualitative way, what we can understand is that the tendency for electron transfer whether it is for oxidizing or reducing, we can arrange. So, if we go for all these species, because this and this, we are talking about their corresponding acceptance of electron, that means E minus they are accepting, that means their oxidizing strength, we are talking in terms of their thing, that how we get the corresponding E0 values. So, this particular thing is there in all standard books, and it has been taken from your analytical chemistry book of Skoog's. So, Skoog's book will tell you that this particular qualitative informations what we can gather from arranging these particular cationic species. Now, we have considered this, and this as their E0 is your standard electrode potential. And that standard electrode potential we have to determine, and how we determine that is a very simple one, that E cell we have to measure, and with respect to your hydrogen potential we have to measure the corresponding one for the second species. That means, this one will go for its corresponding reduction, that means silver 1 will go for your silver 0. So, this reduction, that means the reduction potential for its corresponding reduction of silver ion to silver can be measured if we consider the corresponding standard electrode potential for this, and by definition what we can do, we can standard hydrogen electrode, not the corresponding normal hydrogen electrode, is now standard hydrogen electrode. If we attach, that means this is the junction potential with that of our silver ion concentration, where the activity of silver ion will be equal to 1.00 or 1, and with silver. So, silver ion is dipped into the silver solution, and if we connect these, the corresponding potential we get, and when we is almost open, is not electrolytic cell, but it is the galvanic cell. So, the galvanic cell will record the corresponding potential, which is plus 0.799 volt. So, what we find that this particular one, we have seen that compared to your hydrogen, that means hydrogen is going for its reduction from hydrogen ion, and silver is also going for its silver ion to silver 0. So, what we see that the corresponding oxidizing strength of this, that means Ag1 plus, that means Ag plus is stronger than your H plus. This we have seen from our qualitative picture. So, this will have the tendency, that means the reduction potential of this we can consider. So, this is a different one. So, silver 1 plus is a stronger oxidizing agent than your H plus. So, as oxidizing agent, silver ion is stronger than your H plus. But when we are considering this in terms of its corresponding reduction potential, we see that it is plus 0.799 volt. That means, it can function as a stronger oxidizing agent, that means the cationic version, that means the cationic form of the species which are engaged in the half cell is the stronger oxidizing agent, because you have a corresponding positive potential. So, if we consider this as the measured potential, the standard electrode potential for the silver half reaction is we can measure. For a particular reaction, what we see that now is, therefore, you have this will have more tendency, will react with basically hydrogen gas, giving rise to the corresponding reduction of silver as solid and 2 H plus. So, this is the corresponding cell reaction what we get, and the measured potential what we will be getting. So, now we write the corresponding potential is this one. So, what we get this particular entry. So, this potential we get from there, and we get this potential as your plus 0.799 volt. So, this will be your corresponding potential for silver electrode. Similarly, if we go for the corresponding cadmium electrode, so cadmium is as the corresponding solid. So, this corresponding one and this comparison we all know that cadmium as solid which can now react with this proton, because cadmium on the other sides, because the cadmium is here now. So, this corresponding combination of these things. So, the corresponding electrochemical table, what we know that the silver in one direction, that means silver, if silver is above H plus, then cadmium will be below. So, the reaction will be different one which is opposite to that of the silver reaction. So, we get this as corresponding cadmium as cadmium 2 plus and hydrogen as the corresponding gas. So, what we find from there, the cadmium electrode is now a negative electrode with respect to the standard hydrogen electrode. So, this will be now your negative electrode with respect to standard hydrogen electrode. So, we get therefore, the corresponding potential we can measure and the corresponding E0 value for this cadmium 2 plus to cadmium will be a negative potential 0.403 volt. So, you see the position of these two will immediately tell us that one is the positive potential and another is a negative potential. So, this particular negative potential can be experimentally determined. So, that is the thing that what we are trying to discuss over here is that how we can go for the corresponding tendency and we get this particular cadmium as the corresponding negative electrode. Similarly, we get this particular one as the corresponding electrode for zinc when the zinc electrode is dipped inside a zinc solution. So, zinc 2 again having activity 1 and this can develop a potential of minus 0.763 volt. Again this can be your negative electrode and this will be your corresponding potential. So, the left hand electrode is paired with SHE. Now, SHE will be on the right hand side. So, what we have seen earlier is your SHE on the left, now your SHE will be on the right hand side and your cadmium as well as the zinc electrode will be on the left. So, what we get? So, this left hand electrode paired with the SHE on the right. So, SHE on right, the corresponding combination of these and this will be your E0 for zinc 2 plus and zinc. So, wherever the position is, but the corresponding potential will be writing as its corresponding standard reduction potential. And this reduction potential we see if we consider that is more negative compared to your cadmium. So, this particular one we get for the total evaluation of E cell is therefore your E right minus E left. So far we are not considering, so whether you have the SHE on the left or SHE on the right. So, SHE values equal to 0.0 volt we are subtracting or we are just adding. So, that will not give us the corresponding problem, but when we get that for the silver we have seen that for silver the E0 for the silver electrode is basically minus E of SHE, because the standard hydrogen electrode was there in the left and the silver electrode was on the right. So, that basically giving rise to the corresponding potential for the silver electrode. So, that way we can generate all these things, we can develop all these things, and now as we have seen the corresponding qualitative picture, we can have the corresponding half reaction and the standard electrode potential in volt, so that we can arrange all of them, that means the silver ion, the hydrogen ion, the cadmium 2 ion and zinc 2 plus ion. And we start from here, that means this is 0.799 volt, this is 0.000 volt, this is minus 0.403 volt, and has been determined as this potential of minus 0.763 volts, so it will be minus 0.763 volt. So, that also gives us the qualitative picture from the reaction itself. What we have found out earlier is that the ordering. So, you have this potential, that means you have the 0.799 volt. That means, if we consider this ordering, so this also tells us the same ordering what we have found out earlier. That means, the silver ion is greater than your proton, is greater than cadmium 2 plus, is greater than your zinc 2 plus. So, these are therefore the conformation and the quantitative values we get. So, these are your quantitative values for standard electrode potentials, and these are universally true for applying these potential for any chemical reaction. So, the relative strength of the different ionic species as electron acceptors, that means oxidizing agent in decreasing order, that means zinc is the weakest and silver is the strongest. So, your ionic species are there, that means these we are considering as their electron acceptors. So, we see that starting from the very concept of your galvanic cell or the electrochemical cell, then what we do, that the same thing we are doing, the dipping of a rod inside the solution is developing something where we basically get the corresponding values of E0 values. So, these are fundamentally leveled with the thing that if we have a standard electrode we can develop, then the standard electrode potential we can generate, where you have the corresponding zinc electrode, zinc rod is dipped inside the zinc solution. So, this is your zinc rod. So, that zinc rod is dipped inside the zinc solution of unit activity is giving rise to some potential. So, these potentials are therefore very much useful to tell us that whether your this particular zinc as the metallic zinc can function as a reducing agent. That is why, because zinc 2 plus is a weaker corresponding weaker oxidizing agent. Similarly, this particular silver ion will be the stronger oxidizing agent, having a potential value, standard electrode potential value of 0.799 volt. So, qualitatively the order what we got earlier can also be established in terms of the corresponding different E0 values and all these things. So, in our next class we will be trying to develop all these things based on some equation which is known as Nast equation, and from those Nast equations how we can calculate out the different E0 values and how those E0 values will be useful to understand any electrochemical reactions that we will see. Thank you very much.